Okay, so you are now live and are being recorded. All right, organic chemistry. When we're talking about organic chemistry, and I'll kind of play fast and loose with the lecture slides because I have my own views on the way organic chemistry should be taught. But organic chemistry is essentially baseline. You're talking about carbon, and hydrogen. All organic molecules have some combination of carbon and hydrogen, and then you start adding other things on, okay? And the question sometimes comes up, why carbon? Why is everything carbon? Carbon this, carbon that, which is a legitimate question. Not unlike the question is, why water and everything? It's because what's available, and it's an ideal molecule to serve as a solvent at the temperature range that we find ourselves in. But if we go back to our periodic table, let's see, get that tilted right, periodic table. If you look at group 4A, carbon is able to form the maximal number of bonds with other molecules, which is 4. Okay, since it has 4 valence electrons, it can form 4 bonds. And just like if you're building something with Legos or something, like the more places, the more ways you have connect them, the more interesting and complex things that you can build, right? If you go down to something with 3 valence electrons, or no, excuse me, 5 valence electrons on up, you have fewer options, right? Okay, and then to go in the opposite direction, of course, you start taking away possibilities in the other direction as you move down in groups. And then also abundance. So there's a fair amount of carbon. There are other things that can form 4 bonds, like silica, right below it there, just one period down, but in the same group. But silica is larger and won't form as strong as covalent bonds as carbon because it is larger. The valence electrons are further out, and so the bonds aren't as strong. So carbon is that is why carbon shows up all over organic chemistry. So organic chemistry is essentially the chemistry of carbon and of life itself. Okay. So we're going to look at characteristics of organic molecules. You'll learn IUPAC, the International Union of Pure and Applied Chemistry. Okay, IUPAC names is what that means. It's just the name we've all agreed on as chemists on how to represent organic molecules. So we're all speaking essentially the same language. Okay, so it's like learning a new language. It's like your first day of Spanish 101 if you got to take that in high school. And then you'll be able to name these structures, and draw these structures in various way: condensed form, expanded form, zigzag form, all these things. And we'll also look at alkanes, alkynes, and alkenes. Believe it or not, by tomorrow, when you're ready to head home, you're going to at least have some idea what all of these words mean. Condensed structural formulas, of course, cis and tran, and we're definitely going to look at benzene towards this because it is an extremely important molecule that will have a ring molecule, and look at the aromatic compounds. This takes us back to benzene, of course. Okay, a little preview, upcoming features. So organic compounds is a study of carbon compounds, all right? And they do not typically mix, the ones that are just carbon and hydrogens do not mix with water because, if you remember from our solutions lecture, like dissolves like, polar dissolves polar molecules, and water is a polar molecule. And organic compounds, until you start adding substituents. So we got our partial negative charge up here. That is a polar molecule, water. And then you have a carbon molecule over here that is nonpolar. So they do not dissolve, okay? And that's why, amongst other things, why we have such a mess when a tanker gets a leak in it. Doesn't mix with the water, so it can't be in solution, and it's lighter than water for the most part, so it floats on top as a non-mixed film. And that's also the reason why if you see oil in a puddle, it's so beautiful, because you have the refraction of the of light through the oil and then off the water, breaking up into rainbows. It's all dependent on the organic molecules not mixing with water. Okay, so not soluble. All right, so as a reminder, to differentiate between organic and inorganic compounds, we've certainly looked at a fair number of inorganic compounds, such as salt, sodium chloride. Notice not a carbon in sight in sodium chloride. And something like propane, C3H8, that is carbon and hydrogen, certainly an organic molecule with all of the properties of an organic compound. And we've looked pretty extensively at this point at the properties of inorganic molecules. They dissolve in water, form anions and cations, yada, yada, yada. Okay? All those things that we've come to know about inorganic chemistry. Okay, so examples. So these are the bonding in organic molecules is mostly covalent. Okay, as opposed to inorganic compounds, you have a mixture of ionic and covalent compounds. Remember, that's either taking electrons all the way to fill up valence shells and then forming a bond, or the mixture of electrons to fill up valence shells in the covalent bonds. And the covalent bonds are much sturdier, okay, because you're actually like mixing, you're sharing. Shared custody of the electrons, right? And so then you get, because they're stronger, the melting points and boiling points follow along with that bonding. And the solubility, of course, follows from the polarity or non-polarity of the molecules that are organic and inorganic. Okay, so there's a little list, and I think I'll just go through that. So if you have a high melting point, you're looking at an inorganic molecule, not soluble, organic. That is certainly an organic molecule with carbon and hydrogen. There's C. Magnesium chloride is inorganic. If you'll notice, we have metal, non-metal, okay, ionic bonding there, burns easily, and we'll look at that because we have looked when we were balancing equations. We saw combustion. Combustion always had, hopefully I'm tickling your gray matter here, we always had an organic molecule in conjunction with oxygen forming water and heat, okay? And covalent bonds, always has covalent bonds, is organic molecules. Okay. So I'm not going to get too much into shape. I don't have time to get in the shape of molecules, and we don't have little play sets to like stick these sets together. So some of you who have maybe taken chemistry before, you remember getting out like the Tinker Toy sets and sticking them together. And based on the physical properties of the bonds and the molecules, you're able to visualize sort of what these look like. It's not really what they look like, but it's a useful approximation for us when we're thinking about these compounds. But suffice it to say that all molecules have a shape, and you can visualize that by looking like we have carbon is tetrahedral. All the positives on the hydrogens are pushing away from each other equally, so you end up with that tetrahedral shape. Likewise with the, we have ethane here, 2 carbons. Okay, so let's have our first introduction of the ways that we are going to talk about and represent molecules in organic chemistry. All right. So we have our most basic organic compound, methane, which is a carbon. And when you write carbon or organic molecules, you always put carbon followed by hydrogen and the number of each of those, the subscript. So methane has one carbon bonded to 4 hydrogens, just like that. That is the IUPAC name for methane. Okay, and let's see if we remember. Carbon, of course, has its 4 valence electrons. Okay, remember that from looking at the periodic table, group 4, and hydrogen each has a valence electron. It's willing to share with the carbon. And we've now represented 4 covalently bonded hydrogens to that carbon, forming methane. Okay, and you can imagine how laborious it is to just draw dots all day. So people who do this for a living, they got tired of drawing dots at some point and said, I'm just going to make, to indicate a covalent bond that's right here, I'm just going to draw. Well, we're just going to realize one covalent bond is being indicated with a line, like so. So these two mean the same thing, okay? And the ball and stick model, which we don't get to see, you get a much better idea of what they actually look like physically with the bond angles and all of that there, okay? Okay, so likewise, let's just do another molecule. We have ethane with, I'm just going to put my dots right here, bonded to 3 molecules, and then in this case, it's bonded to another carbon. Boom, boom, boom. Ethane, much easily bonded. Carbon always is filling up its valence shells with 4 bonds, right? 1, 2, 3, 4. 1, 2, 3, and 4. Okay? And let's see. Get rid of all of those my messy numbers. There we go. Oh, one more. And then a ball and stick model, of course. Okay. Okay. There is butane. Butane has 4 carbons and enough hydrogens to fill up those 4 needed valence electron shells to make carbon happy and the hydrogen happy there. Okay, and that's just the expanded structural formula, of course, represented by C4, 1, 2, 3, 4, and the 10 hydrogens, 1, 2, 3, 4, 5. Trust me, 10 hydrogens there, C4H10. Okay, so C4H10 is useful, and I'll see, but it doesn't always give you a great idea or exactly what you're looking at. Okay, so that's what, that's hexane. Okay. I'm just going to throw these names around for a bit, and I'm going to get into more how you, yes, you will be able to name these these molecules all by yourselves with a few simple-ish rules, okay? There we have hexane with 6 carbons and 14 hydrogens. You can count them up there. The carbons in black and the hydrogens in white by convention. Okay, and now we're going to look at the IUPAC, International Union of Pure and Applied Chemistry. We're going to be able to write the IUPAC names and draw the condensed structural formulas and skeletal formulas, which I haven't talked about yet, but skeletal formulas are even a simpler way to represent these molecules for people who have to draw them all day, every day, draw these huge formulas of drugs and stuff. Yeah, but skeletal formulas and of the alkanes and cycloalkanes is where we're going to start. All right. Everyone hanging in there okay thus far? Okay, great. Now let's do the fun stuff. So alkanes. Alkanes are hydrocarbons that have the following: only carbon to carbon single bonds and carbon to hydrogen single bonds. Those are alkanes by definition. Okay, single bonds. You'll never see a double bond in an alkane. If it's got a double or a triple bond, you no longer have an alkane. Okay. This is something that you should commit to memory. This is slide 17. And what they are is the prefixes that we're going to use in the naming, not just of the alkanes, but any organic molecule that we have to name. Okay. Prefixes for 1 is meth, 2 is eth, 3 is pope, 4 is bute. And after that, we just are basically using the Greek forms of that. You probably have seen before. 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is non, and 10 is dec. Okay? The only really tricky ones are the first 4, meth, eth, prop, and bute. 1, 2, 3, and 4, meth, eth, prop, and bute. Just memorize them. Use a mnemonic if you want, because you don't want to be looking these up all the time. You can, but it's going to slow you down so much. It's just going to become very cumbersome. So know that in 1 carbon meth, 2 carbons eth, 3 prop, 4 bute, pent, hex, hept, oct, non, and up to dec. And that's fine. We get up to 10. It goes up from there, obviously, but this will be fine for us. This will give us a great foundation. Okay? So yeah, that'll be fine. But like I say, just trust me, it's going to be easier for you. Maybe have that as a backup. But just to make it easier for you, I would suggest just learning to count to 10 in organic. Like learning to count to 10. And that's like the first thing you use. And you learn when you're learning a new language, right? Uno, dos, tres, cuatro, cinco, siete, all of that. It's just easier than like, oh. But to answer your question, yes, you can have it as a backup, but you'll probably learn it just by the repetition getting pounded into your brain. So, yeah, absolutely. Condensed. And speaking of, anyone, I should probably check and make sure that no one is trying to get in. No. Okay. Okay. So a condensed structural formula is when you take the carbon and the hydrogens, okay, and just write them and then indicate the carbon to carbon bond with a line. Okay? So for instance, in butane, the condensed structural formula, 1 carbon, 3 hydrogens, 1 carbon, 2 hydrogens bonded to the next carbon and 2 hydrogens, and the last carbon with 3 hydrogens. So butane. Okay, 1, 2, 3, 4 carbons. Okay, so this is the condensed structural formula. The expanded, and I'm going to give myself a little, the expanded version of this would be the following. Again, you have carbon to carbon to carbon to carbon, and then you expand it by indicating the hydrogen to carbon covalent bonds. Those are the two same things. This is the most time consuming. The first one is the most time consuming. Then we have the condensed version, which you can write out a lot more quickly. And then I'll get to the other ways of representing this. And I'm not even going to bother with doing the dot version of this. That would just take too much time, and it's never done by organic chemists. Never is an overstatement. Rarely is it done. You'll either see the expanded, you probably see the condensed, and sometimes you might see the expanded. Okay, so here we have a carbon in expanded form, bonded to 3 hydrogens. We have CH3 bonded to another carbon in the condensed form, the expanded, and once again the condensed. Okay. Now here is skeleton. All skeleton is saying you draw a zigzag, and each bend in your zigzag is a carbon molecule. So if you have, for instance, butane, we have 1, 2, yeah, 1 carbon up to the 2nd carbon, down to the 3rd carbon, up to the 4th carbon. Okay. If they aren't indicated, the hydrogen bonds to those carbons are a given. So this is a skeletal version of butane. These are all representations of butane with their 4 carbons. Okay, we have 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. And in the skeletal, you don't do stuff like draw in the hydrogens or anything like that. That's a no. That's nonsensical. The skeletal version of butane is this right here with its 1, 2, 3, 4 carbons. See? Chemists are lazy too. You know, if you can get away with shorthand and communicate, things are going to get more and more esoteric, I guess. Well, just like with languages, or yeah, been doing this since Egyptian times with hieroglyphics, I guess. Exact type of thinking, just in science terms. Okay, so expanded, condensed, and skeletal versions of the same molecule, butane. Okay. Hexane, yeah, ball and stick. I'll just go through some ball and stick. Expanded structural, condensed structural, okay, and skeletal versions of hexane. Hexane, because it has nothing but carbon to hydrogen bonds, single bonds, with 6 hex carbons. 1, 2, 3, 4, 5, 6. Okay, and you can see way up here on the right, we have hexane indicated by 6 carbons and 14 hydrogens. And then you can represent it in those following 4 or 5 different ways. I guess a condensed structural is kind of the same. Just one is a straight line, one is kind of trying to indicate the shape. But, okay, C6H14, if you want to, you can count the carbons and the hydrogens, but trust me, hexane adds up to C6H14. Okay, so nothing but carbon to carbon and carbon to hydrogen single bonds in your alkanes. Okay, Kane, and the prefixes 1 through 10, meth through doc. Okay, and this looks like pretty much a repeat of what I did. The expanded structural formula of butane, the condensed structural formulas of butane, and the skeletal versions of butane down here on the very bottom. Okay, ANE for your alkanes. You're always going to end with the prefix that's given based on the number of carbons, and you're always going to end with an alkane with ANE. The suffix ANE means that you're going to have nothing but single covalent bonds to carbon and hydrogen. Okay, so let's look at this example and see how we are tracking. Okay, so given the following expanded structural formula, provide the molecular formula. Okay, molecular formula, okay, is both obviously the carbons, 1, 2, 3, 4, 5 carbons. So we know it's C subscript 5, and the number of hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 12, C5H12. Okay, molecular formula, C5H12. The condensed structural formula, CH3 to CH2 to CH2 to CH2, 1, 2, 3, 4, to CH3. Okay? Condensed structural formula and the compound name. Now, here's the tricky part. Could anyone, after all of my instruction, do you already know what the name of this compound is? Okay. So I will tell you. So we know what we need to start with is at the number of carbons. There are 5. The prefix, and we know it's an alkane, right? There's nothing but single bonds. So we know it's an alkane. We know it has 5 carbons. The prefix is pent. Okay, from slide 17, I think it was. Pent with the suffix ane. So that is pentane, that is pentane, that is pentane, and I'll just do the skeleton. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That is pentane as well, as long as we're going through all of our options. Okay. Exactly. Precisely right. You nailed it. And then practice, practice, practice until it started to become. Then you can kind of look at. Eventually, you do this enough times, and you'll just look at these, and it'll be like reading a page out of a book. Oh, that's cyclohexane, difluoride, blah blah blah, and you don't even really think about it. Okay, or reading sheet music for the musicians about there. Okay. Okay, so pentane, yes, indeedy. Yeah, we got through that. Okay, so let's look at this from there. So we're given ethane. Okay, we want the condensed structural formula for ethane. So that's 2 carbons. Ane means it's all saturated. Saturated means single bonds involving 2 carbons. So we know condensed structural formula. So we have a carbon and a carbon. And you can draw the expanded first if it helps you. 1, 2, 3, 1, 2, 3. But they didn't ask for that. They asked for the condensed. So we know that each carbon is bonded to 3 hydrogens. There we go. Ethane. Okay. Heptane, same thing. 1, 2, 3, 4, 5. So we're going to have CH3 to CH2 to CH2, CH2 to CH3. Double check. 1, 2, 3, 4, 5. Yes, indeed. And nothing but single bonds. You can draw the expanded version if you want to put your mind at ease about that. All right. And well, I may as well do the name as well. So we have C2H6, and here we have C5H2, 4, 6, 9, 12, H12. Actually, I don't know why I put 3 there. It should be a 2. There we go. C5H2, 12. 2, 4, 6, 12. Yep. Okay. It is heptane, yes. Oh, pentane. Oh, shoot. You know what? You're right. Thanks for that, guys. So, see, there you go. That's another reason. So, heptane is 7. Good catch, Derek. Thank you very much. So, let me do that correctly. I did pentane. Would it be CH3, CH2, 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 1, 2, 3, 4, 5, 6, and we can go down. That's legal. CH3. 1, 2, 3, 4, 5, 6, 7. There's your heptane. Good call. I make that. That warms my heart that you were able to catch that and follow along. Nicely done. All right. And you know what? I will pick it up with cycloalkanes tomorrow. Yeah, we'll call that good. Any questions on this material? Okay, not too bad. Okay, so I'm